Hello everybody! I'm finally getting around to finishing this video in chapter 8. Sorry it took so long. I had some, let's just say, some challenges. So what I want to do is just quickly finish chapter 8, tell you the important things, and then do a couple example problems. So keep in mind, chapter 8 is not really much new information. It's really just Newton's laws for something which is moving in a circular path. For something that's moving in a circle or a circular path, we know the acceleration is given by v squared over r, where v is the speed in meters per second, v is the radius of the circular path. V squared over r gives us the magnitude. The direction is always towards the center of the circular path. So really all we have is just Newton's laws. The sum of the forces equals ma, and one of those forces is going to be in the radial direction, which basically means towards the center. So it's either going to be the sum of the forces in the x direction or the sum of the forces in the y direction. And if it's moving in a circular path, we know the acceleration is v squared over r. So the sum of the forces towards the center of the circular path equals mv squared over r. Only other real new thing, or not even new, but an object can be accelerating because of either a change of speed, a change of direction, or both. Acceleration because of a change in speed is called tangential acceleration. Acceleration because of a change in direction is called radial acceleration. They are always perpendicular to each other, which means that if I'm calculating the total acceleration, I can just use, in essence, Pythagorean theorem. So if something's moving, let's say in a circular path, let's just say in this case it's going, what is that, counterclockwise. And if I'm right here, whoops, the velocity is always tangent to the path. The acceleration is always, for circular motion, towards the center. Now, the tangential acceleration direction depends upon whether the object is speeding up or slowing down. So in this case, let's say the object was speeding up, then we would know that the tangential acceleration points in the same direction as the velocity. If the object was slowing down, tangential acceleration would point in the opposite direction of the velocity. Okay, so let's just look at some of this stuff from chapter 8. So one, I didn't really cover this for orbits, but if an object is moving in an orbital path and gravity is the only force acting on it, then basically the sum of the forces equals ma. In this case, the only force is the force of gravity, mg. The object is moving in a circular path, so we know the acceleration is v squared over r. And then if you just end up solving for v in this case, you get the square root of rg. Now this also is the critical speed. This comes up a lot, this square root of rg. This is the critical speed in which something is going to maintain contact with the surface. So this critical speed comes up in, let's say an object is cresting a hill. This is the maximum speed it could go over the hill and still maintain contact. Or if something is moving in a loop-de-loop, where it's not connected to the track, then this critical speed is the minimum speed at the highest point here, where the object is still going to maintain contact with the surface. Okay, a couple of these important concepts. This RTZ coordinates, where R is towards the center, T is tangent, and Z is in the Z axis. I'm not covering this. Oops, you don't really need to do this. Sometimes it's nice, but we're just using the sum of the forces equals ma. One of those components, either the x or y, is going to be towards the center of the circle. Now the acceleration is v squared over r. Projectile motion, don't really worry about that for this chapter. Other things. So like I said, we're not really going to be looking at stuff expressed in RTZ form. So we're really just looking at sum of the forces in the x direction equals max. Sum of the forces in the y direction equals may. Just keep in mind one of these components is going to be towards the center of the circular path. We know the acceleration is v squared over r. So uniform circular motion basically means the speed is constant, moving in a circular path at a constant speed v. If that's the case, there is no change in speed, so there is no tangential acceleration. The only acceleration we have is centripetal acceleration. Non-uniform circular motion is one in which the speed is changing, which means I have a tangential component, either in the same direction or opposite direction of the velocity, and a radial component towards the center of the circular path. So again, let's just say I'm moving in a circle. That's a horrible circle. Let's say I'm moving in a circle, and let's say I'm moving clockwise, and let's say at the very bottom, I am slowing down. The question is, in which quadrant is the acceleration? So let's say, I'm moving clockwise. My velocity at the very bottom, in this case, is pointing to the left. Radial acceleration is always towards the center of the circular path. So the question is, if you are slowing, I don't remember if I said slowing down or speeding up, but let's say you are slowing down. If that's the case, in which direction, in which quadrant is the total acceleration? I'll give you 30 seconds. Okay, so if I'm slowing down, that means my acceleration is in the opposite direction of the velocity. So in this case, since the velocity is to the left and I'm slowing down, my tangential acceleration would be to the right. So if I have a component of the acceleration to the right, a component straight up, then my total acceleration is going to be in the first quadrant. And that's really all there is to chapter 8. Circular motion, using Newton's laws when something's moving in a circular path, and we just know the sum of the forces is mv squared over r. So let's do a couple problems and then we're done chapter 8. So the first, let's take a look at conceptual question 8.5. It says the figure below shows two balls of equal mass moving in vertical circles. Is the tension in string A greater than, less than, or equal to the tension in string B if the balls travel over the top of the circle with equal speed? So one, let's just draw a Freebody diagram. At the very highest point, I've got two forces acting. I've got tension straight down, and I've got gravity, mg. And in this case, we are moving in a circular path. We know the acceleration points towards the center, which in this case is straight down, and the acceleration is going to be v squared over r. So if I do sum of the forces in the y direction equals may, I'm going to define down as positive in the y direction. Again, I think it's a good idea to always define positive in the same direction as the acceleration. So what I get for the sum of the forces in the y direction is tension plus mg equals mv squared divided by r. So my tension is mv squared divided by r minus mg. So balls have the same mass, they have the same speed, so the only difference is in the radius of the circular path. Since the radius for B is greater, what I can see here is that if I have a greater radius, that's going to make this number smaller, which means I'm going to have a smaller tension. So in this case, the answer is the tension in case A is greater than the tension in case B, because for B, the acceleration, which is v squared over r, I've got a bigger radius, so I have a smaller acceleration. End result is I'm going to end up getting a smaller tension for part B, or case B. Okay, let's take a look at 856. This is a really great problem because it combines both circular motion and projectile motion. So a 100-gram ball on a 60-centimeter long string is swung in a vertical circle about a point 200 centimeters above the floor. Tension in the string when the ball is at the very bottom is 5 newtons. A very sharp knife is suddenly inserted, as shown in the figure below, to cut the string directly below the point of support. How far to the right of where the string was cut does the ball hit the floor? So because of the way this knife is set up, this is going to be cut when this thing is at the very bottom, and, well, end result is this thing is moving to the right with some velocity v. What we're going to do is use circular motion to figure out what is the velocity at the very bottom, and then from that it just becomes a projectile motion problem. So if I draw a free body diagram, the object is at the very lowest point. What I have are only two forces. I've got tension acting straight up, and I've got gravity, mg, acting straight down. In this case, the acceleration points towards the center, which is straight up. So the acceleration is v squared over r, straight up. So if I do the sum of the forces in the y direction equals may, what I get is tension minus mg equals mv squared over r. So we've got the tension, we know the mass, we know the radius, we can basically just solve for v. Let me actually grab my solution so I have the numbers. So we're going to solve for v. So basically I'm going to multiply both sides of this equation by r, divide by m, and we get r times t minus mg divided by m equals v squared. So solving for that, what we get is, where's this? V is equal to the square root of the radius times tension minus mg divided by the mass. So we have all of these values. Let me just skip the step of writing out the numbers, which you'll get if you plug in. The radius is 60 centimeters, 0.6 meters. Tension is 5 newtons. The mass is 100 grams, so 0.1 kilograms. Put it all together, and what you're going to get is the speed is 4.91 meters per second. So that's how fast this is going right at the very bottom when the string is cut. So now this becomes a whole new problem, in essence, where I have an object. Whoops. I have an object which is at an initial height of 200 centimeters minus 60 centimeters. So it's at an initial height of 1.40 meters. This thing is launched horizontally with an initial speed of v naught x, which equals 4.91 meters per second. So keep in mind, if this thing is launched horizontally, there is no velocity in the y direction to begin with. So what I have here is basically just a projectile motion problem. Something is launched horizontally from an initial height of 1.4 meters, traveling at 4.91 meters per second. How far away does it land? So if I set up my y equation, I have y naught equals 1.40 meters. Y equals 0. V naught y is 0 meters per second because this was launched horizontally. Vy we don't know, but we don't need. We know acceleration in the y direction is negative 9.8 meters per second squared, and t is what I'm looking for. The equation that we have is y equals y naught plus v naught yt plus 1/2 ayt squared. Y is 0, v naught y is 0. What I get is t equals the square root of negative 2 y naught over ay, which when I put in 1.4 meters, negative 9.8 meters per second squared, what you're going to get for the t for the time is 0.535 seconds. So that's how long it takes before it hits the ground. Now if I want to know how far away it lands, I basically just know that for x, we really only have one equation. X equals x naught plus v naught xt. I can let x naught be 0, so I just get x equals v naught xt, which is 4.91 meters per second times 0.535 seconds, which you're going to get, move this down, what you're going to get is x equals 2.63 meters. All right, so just sort of going back and reviewing this one more time. Let's change this to a highlighter. Actually, let's change this to green. Okay, so in this problem, we have something moving in a circular path. We're given the tension at the bottom. So from the tension, we can figure out what the speed is, and then it just becomes a projectile motion problem. We're looking at this down at the very lowest point. At that point, the object is moving to the right. Again, we can get the speed from Newton's laws. Sum of the forces in the y direction equals MAY. Whoops. Whoa, what just happened there? Oh, I just erased something. Oh well, sum of the forces in the y direction equals MAY. If I look, the only forces we have are tension straight up, gravity straight down. The center of the path is straight up when I'm at the lowest point, so my acceleration in the y direction is v squared over r. Doing sum of the forces equals ma, I get tension minus mg equals mv squared over r. Solving for v, plugging in the values, we get 4.91 meters per second. All right. Now it just becomes a projectile motion problem. Sorry about that. So something is initially traveling. Well, that was fun. Sorry about that. Technical difficulties. I forget where I ended up being. So let's just do this again. We figured out that the speed from using Newton's laws and sum of the forces equals mv squared over r was 4.91 meters per second. And now it just becomes a projectile motion problem where the situation is I've got an object which is launched with an initial speed of 4.91 meters per second at a height of 1.40 meters. We wanted to know how far away it lands. So the first thing we got was the time in the air from the vertical motion, and then the horizontal motion, we just used initial velocity in the x direction times time. Okay, let's go back to this very last example problem, 8.29. So in this problem, an 85,000 kilogram stunt plane performs a loop-the-loop, flying in a 260 meter diameter vertical circle. At the point where the plane is flying straight down, its speed is 55 meters per second, and it is speeding up at a rate of 12 meters per second per second. A, what is the magnitude of the net force on the plane? You can neglect air resistance. B, what angle does the net force make with the horizontal? Let the angle above the horizontal be positive and an angle below the horizontal be negative. So this plane is performing a loop-the-loop. Now, it doesn't tell us whether it is moving clockwise or counterclockwise, so let's just assume that the plane is moving counterclockwise. It says at a point where the plane is flying straight down. So that means we're at this point right here. We know its velocity points straight down. And it's speeding up at a rate of 12 meters per second. So one, it's moving in a circle. So we know it is accelerating. And in this case, the radial acceleration points towards the center of the circular path. And we know it's going to be v squared over r. In terms of the tangential acceleration, it is speeding up, which means that it is accelerating in the same direction as the velocity. So we know the tangential acceleration in this case is going to point straight down, and it's increasing its speed at a rate of 12 meters per second every second. So we know this tangential acceleration is 12 meters per second squared straight down. My radial acceleration is going to be v squared over r. So let me define my axes such that we have basically the x-axis is positive to the right, and let's just make the y-axis positive straight down. Okay, so again, we're just using Newton's second law. Sum of the forces equals ma, but we're going to break this up into two components. And in case, we're just going to look at sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may. In terms of the acceleration in the x direction is v squared over r to the right. Acceleration in the y direction is 12 meters per second squared straight down. So let's just use Newton's laws and figure out what the acceleration is. Let me see if I've got the answers so I don't have to get all this done. Calculate everything in my head. Okay, so let's first look at the sum of the forces in the x direction equals max, which is going to be mv squared divided by r. We have the mass, we have the speed, we have the radius. So actually, let's just plug in the numbers. So we've got 85,000 kilograms. The speed, what was the speed? 55 meters per second squared divided by the radius, which is 260 meters. What we get is the sum of the forces in the x direction is 1.978 times 10 to the 6 newtons. So this is the force in the x direction. Now if I look at the sum of the forces in the y direction equals may, again, we got the acceleration was 12 meters per second squared straight down. So what I have is the mass, 85,000 kilograms. The acceleration is 12 meters per second squared. What I get is the forces in the y direction is 1.02 times 10 to the 6 newtons. So this is straight down, where the sum of the forces in the x direction we got to the right. So in essence, what I have is my force in the x direction to the right is positive 1.978 times 10 to the 6 newtons. And the force in the y direction points straight down, so that would be negative 1.02 times 10 to the 6 newtons. So in essence, what we have are the x and y components of a vector. In this case, it's a force. So if I want to know what is the magnitude of the force, it's going to be the sum of fx squared plus fy squared, which once you put in those values, what you'll get is 2.2 times 10 to the 6 newtons. That is the magnitude. And in terms of the angle, we're going to do inverse tangent of the y component over the x component. Once you plug those in, what you'll get is negative 27 degrees, which is in the fourth quadrant, which is what we expect for a positive x component, negative y component. Woo! All right, that is it. We are done chapter 8, and I'm going to send out a video update tomorrow, but we're moving, or maybe tonight, but soon, moving to mastering physics to do our online homework collection and quizzes. Hope you're enjoying spring break and getting a chance to relax. I wish I could tell you I'm relaxing, but I'm not. I'm scrambling trying to figure out how to do online quizzes and stuff like that. So stay tuned and stay healthy. That's it.